Hello everyone, in this video we'll discuss about the viscous damped systems. So dampers are the energy dissipating elements, and the dissipation of energy may take place in the form of the heat or noise. And there are various methods of energy dissipation. Viscous damping is one of them. As the name suggests, viscous damping uses the fluid as a means for energy dissipation. The fluid can be air, water, oil, or any other fluid. Now this viscous damping, it is widely used in various applications, and the damping is done in two ways. In one way, what we exactly do, the flow of high viscosity fluid, it takes place through large openings. That is called as the laminar flow viscous damping. They are also called as the dashpots. In other one, the low viscosity fluid, it passes through small openings. That is called as the turbulent flow viscous damping. And this turbulent flow viscous damping is usually used in the shock absorbers of automobile suspension system. So the viscous damping, it finds its application in the automobiles, their shock absorbers. They can also be used in the piping systems, in buildings, in the flow systems, and various applications. And there may be various methods in which the viscous damping can be studied or analysis can be done. But in this case, or in this video, we are only talking about the linear viscous dampers. Now what do we mean by linear viscous dampers? These are the dampers in which the damping force, which we are denoting by F suffix D. So this damping force is linearly proportional to the velocity of the movement, velocity of the flow, or velocity of the movement of mass of the body. By this we mean that the velocity, the faster the velocity with which the mass is moving, more will be the damping force which resists the motion. So here we can see there is a piston cylinder assembly which is fixed at one end, and this piston has got fine holes drilled through it, right? I told you initially also that whatever is the damping done in case of the viscous systems, it is done through the flow of the fluid, and from where the fluid flows, it flows through the holes. The holes may be the large or the small ones, depending upon the kind of flow we want, but there are fine holes that are drilled in the piston, and through this the fluid, it passes to the other side of the cylinder. Now in this case, what exactly we are doing, we are applying force in this direction, right? We're trying to pull piston in this direction. So what happens, this whole system, it moves in this direction, and when the whole body is undergoing force in particular direction, what exactly happens? Now because the fluid, right, the fluid is incompressible, so it has to move somewhere else. So through the openings in the piston, it moves on the other side of the cylinder. If we want to find the velocity of fluid that passes through the piston, right, through the openings in the piston, what it will be? We know the continuity equation, which is velocity into area. So what is the velocity? And okay, let's assume that the area of the cylinder is A, and the area of all the holes, because there are number of holes drilled in this piston, so the area of the holes combined, let's assume that is A naught, right? So the velocity of fluid will be equal to velocity with which the system is moving, right? So it is x dot A upon the area through the holes A naught. It will give us the velocity of the fluid which is passing through the piston, through the holes in the piston, right? Now what exactly happens if we talk about any body, or if we talk about the piston, what is happening? In this we can see that the fluid at this end, it is applying pressure on this way on the piston, right? And the fluid on the other side, it is applying pressure on the piston on this side. So this is the region. The region, let's assume the A region is the region of high pressure, and the region B is the region of low pressure, right? So there is the pressure difference in the system. So that pressure difference, let's say, is delta P, which is PA minus PB, the difference between pressure on the higher side and the lower side. And this is equal to what? Let's assume some resistance is being applied by the piston to the flow of the fluid. So let's assume that R is some resistance, and that this resistance is dependent upon a lot of factors, upon the viscosity or the area or the design. So on a lot of factors this resistance is dependent. So let's assume there is some force which is applying, which is offering resistance. So this change in pressure or the difference in pressure is equal to R into V. V is what? The velocity with which the fluid is moving, right? Let's say some velocity with which fluid is moving. So it is R into V. So what is this? This is the damping force which we are denoting by Fd. So the damping force is what? It is difference in the pressure, right? So force is what? It is pressure into area. And what is the total pressure on the system? It is the difference of the pressure on the higher side and the lower side. So it is Pa minus Pb into area of the cylinder. Now see, there are a lot of areas included in the system. In some systems you'll say that at this end, if we see that the total area is less because there is this area of this rod as well, this area of the rod, but we are ignoring this area to make the equation easier. So we are assuming that, let's say that area on both the sides is same, there is no difference in the area. So therefore this equation becomes Pa minus Pb into the area of the cylinder, right? And what is Pa minus Pb? It is R into V. And what is V? We calculated here, which is x dot into A upon A naught. So the equation becomes R into A square upon A naught into x dot. So from this equation, what exactly we have deduced is the damping force is directly proportional to the velocity of the flow of the fluid, right? And if we remove this proportionality sign, we get a constant which is C, that is the damping coefficient. So we get a coefficient, and this small c is the damping coefficient. So therefore the damping force is equal to damping coefficient into velocity of the fluid. So this is the system that we'll take up for studying the effects of the dashpot, right, or the damper. So dashpot is basically the damper in which high viscosity fluid flows through large openings, right? So let's take a spring and damper which are fixed at one end, right? And we are showing that some mass is being attached to this damper and the spring, and the equilibrium position is C. So what these equilibrium positions A, B and C are showing, initially when there was no mass, the spring and dashpot, they were at the position A. When the mass was being added, so of course some displacement took place, some elongation took place. So the new equilibrium position was BB. But when we try to pull the mass downward, then it comes to a new position which is denoted by CC, and this distance is actually showing between B and C, it is showing the displacement of the mass, right? So what exactly happening is the direction of displacement. This is showing the displacement and this is showing the displacement of the mass, right? Now, and the force, that means the force that is acting in the downward direction. So the acceleration is acting in the, so displacement is in downward direction, velocity will be in downward direction, and acceleration will also be in the downward direction. So if we try to find the equilibrium position for this whole system, it will be mass into acceleration of the body, right? That is the force with which it is moving downward is equal to minus of C, that is the damping coefficient, into the velocity minus the spring constant into the displacement. Now, because the motion is taking place in downward direction, therefore the damping force and the spring force, they'll act in the opposite direction. So this is the equation, and if we bring all the terms on one hand, we'll get this equation, which is mx double dot, which is mass into acceleration, plus c into x dot, which is damping coefficient into velocity, plus s into x, which is the spring stiffness into the displacement, and that is equal to 0, because we are saying that the sum of all the forces, inertia forces and external forces on the body, it should be 0. In some places we can also write this, you'll see that the equation is written in this way, that the direction of all the forces is in one direction. This is because instead of taking the external force, the inertia force is taken into account. So if this is the direction of the external force, inertia force will be equal and opposite to it. So you'll find at certain places or in some books that it is given that all the three forces are acting in the same direction, because they are not taking the externally applied force, they are taking into consideration inertia force, right? But the values will remain the same and equation that we'll get will also be same. So we can also write this equation. If we want to take this m from this acceleration factor, the equation we'll get is in this way, right? Now if we assume that the solution of this equation, this quadratic equation, is of the form e raised to the power alpha t, right? So what will be the equation? It will become m alpha square e raised to the power alpha t plus, where t is time, right? And alpha is some constant, some coefficient that we have taken, plus c into, so this will be replaced by alpha into e raised to the power alpha t plus s into x will be e raised to the power alpha t. So we are actually replacing x with e raised to the power alpha t. So its velocity will become alpha e raised to the power alpha t, and acceleration will become alpha square e raised to power alpha t. So this is what we have done in this equation, right? Now if we see in the whole equation, e raised to the power alpha t is a common factor, so we can take it common. We take it to the other hand, so this is the equation that we are left with, which is m alpha square plus c alpha plus s. Now, for this quadratic equation, if we want to find the solutions, if we want to find the roots of this equation, they will be, let's say two roots are there. Of course, two roots are there, right? So let's say the roots are 1 and 2. So it will be minus b, right? If the equation is in the form of ax square plus bx plus c, so it is minus b plus minus root b square minus 4ac upon 2a. So same formula we have applied, minus b, which is minus c, plus minus under root c square, which is b square minus 4 into a into c upon twice of a. So this is the equation that we'll get, and we can also write this equation in the form of minus c upon 2m. So we are writing the denominator individually for both the terms. So plus minus c upon 2m, if from this factor we take c common, so because this is c square, so it will be c, and we can also take, then of course we have taken c square common, so for the second term it will also be part of denominator. So this is the root that we'll get. That means one root is minus c upon 2m plus c upon 2m under root 1 minus 4sm upon c square, and other will be with the negative sign. Now for these roots, if we want to write the general solution or the general equation, it will be A, where A and B are constants. So it will be A e raised to the power alpha 1, which is this root alpha 1 into t, plus B e raised to the power alpha 2 into t. And if we write the value of roots in this equation, so alpha 1 is with the plus sign and alpha 2 is with the negative sign. So this equation that we have written for the general solution. Now if we look at these equations, there are three possibilities, right? There are three possibilities. The first possibility is, if we look at this term 4sm upon c square, if this term is less than 1, which means that c square is greater than 4sm. So what will happen? The roots for this case 1, they will be minus c upon 2m, and this c square is greater than 4sm. So the denominator is greater, right? So we'll get a smaller value. So, but this minus c upon 2m and whatever you added this, because the value is very small, so we'll get the negative term. In case of this root, right, also because this is a negative term, this is a negative term, so both the values will get negative, but the roots will be real and distinct, right? Now we can write these roots for this general solution for in first case. So what we'll see, that the system is exponentially decaying, right? and it is a aperiodic motion, which means that the system has got very large values of damping, and this type of system is called as the over damped system, where we have got the exponential decaying of the magnitude of the damping and the aperiodic motion. The roots are real and distinct, so it is the over damped system. The second possibility is that 4 sm upon c square is 1, which means c square upon 4 sm is 1. So if this factor is 1, so it will be 1 minus 1. The second factor will be eradicated. What will be left with? A raised to the power e minus c upon 2m, and same plus b e raised to the power minus c upon 2m. That means both the roots are repeated. We are getting the same roots, and this system is called as the critical damping system, right? And this is also a decaying motion, because if we see at the general solution, it will be a e minus 2c upon minus c upon 2m into t plus be minus c upon 2m into t. So this is also the decaying motion. The third case is when 4 sm upon c square is greater than 1. That means c square is less than 4 sm. So what will happen? We'll get the complex conjugate roots. That means we'll get the complex roots, right? So in this case, what happens? These are called as the underdamped systems, and in case of the underdamped systems, the system oscillates about the equilibrium point. So the system that we discussed, so it had roots, and we can also write this equation for roots in this way, right? So we can also say that this term c upon 2m square upon s upon m, it can be written as the damping ratio, which is zeta, right? And we can also write this equation as c upon 2 under root sm. So what is the damping coefficient, which is denoted by C? The way we have the spring constant, which is S. So we have got the damping coefficient. So C can be written as 2 under root Sm into zeta, right? If we multiply and divide the whole equation by under root S, this is the equation that we get, which is 2S zeta upon omega n, where omega n is the natural frequency of vibration, which is denoted by under root S upon m, right? So we can also write the conditions for the critical damping, over damping and under damping in terms of zeta. So when zeta is equal to 1, it is critical damping condition, because this condition we have discussed that when c square is equal to 4 sm. So when there is critical damping system, c is equal to cc, right? So C is what? The damping coefficient, and Cc is what? The critical damping coefficient. So both these factors are same. So zeta can also be written as the ratio of the critical damping coefficient, damping coefficient upon critical damping coefficient, right? So when this is 1, we say that the system is in critical damping condition. When zeta is greater than 1, it is over damped system. When zeta is less than 1, it is under damped system, right? So this is the diagram for the underdamped system when zeta is less than 1. This is the graph we'll plot if this is when zeta is equal to 1 and this is when zeta is greater than 1, right? So we'll see how these graphs are being plotted. So we've already seen for this equation written in this way, the roots alpha 1, 2 can be written in this way. Now we've also studied what is zeta, so we can replace these roots with the value of zeta, and the equation can be written in this form, which is minus zeta plus minus under root zeta square minus 1 into omega n. And the general solution of the equation is written in this way for displacement, which is x is equal to a e alpha 1 t plus b exponential of alpha 2 t. Now we'll again take into consideration all the three cases that we have discussed till now. The first one was the overdamped system in which zeta is greater than 1, right? So what are the roots alpha 1 and 2? It will be minus zeta plus minus under root zeta square minus 1 into omega n. And if we write the general solution of this equation, it will be in this form, which is a e raised to the power minus zeta plus under root zeta square minus 1 omega nt, and here we will get minus zeta square under root zeta square minus 1. Now the equation says that zeta is greater than 1. So if zeta is greater than 1, this term will be positive and this term will also be positive. But when you are, if here this term is positive, so when we are subtracting this positive term, we will get only the negative term. And similarly, because these are negative terms, so they'll add up and the value will increase. So both the roots that we'll get will be real, distinct but negative, right? And the value of this constant will be greater than that of a. So what we'll get, we are getting the exponentially decaying system. The amplitude is decreasing exponentially and there is large amount of damping taking place in the system. That is why it is also called as the aperiodic motion. So if we plot a graph between displacement and time, this is the kind of graph that we'll take in the overdamped system. The second case was that of the underdamped system where zeta is less than 1. So if zeta is less than 1, we'll get complex roots, and this is how the roots can be written, which is minus zeta plus minus I under root 1 minus zeta square into omega n. And if we write the general solution for this equation, it will be in this way. We'll just replace the values of zeta 1 and zeta 2 with the roots of this equation. Now in this equation we can take this factor out, the common, which is e raised to the power minus zeta omega nt, and rest of the equation we can write it like this, right? We have just taken this term common. It was same for both the factors for with constant a and b. So if we look at this equation, we'll see that there are two different factors. One is this factor e raised to the power minus zeta omega nt. That means the amplitude of the motion, it is decreasing exponentially, right? Because this is negative sign. So what is happening? The motion is the exponential decay system or the decreasing system. But if we look at the second half of the equation, it says that it is the equation of the simple harmonic motion. That means the oscillatory motion is there. So if we look at the graph, that means we'll get oscillatory motion with decreasing amplitudes. With each cycle, we'll see that the amplitude keeps on decreasing and after certain time the system comes to a halt or it stops. So this factor that we are getting, that is under root 1 minus zeta square omega n, right? This is termed as omega d, which is the frequency of underdamped system, and the frequency of underdamped system is always lesser than the natural frequency of the system because amplitude is reducing continuously, right? So what we see that we are getting the imaginary roots and we are getting the oscillatory motion because this part of equation is showing that there is SHM type of motion, and the first part is showing that the amplitude is decreasing exponentially. So what we are getting, we are getting the oscillatory motion with decreasing amplitude. The third type of the third case that we saw was the critical damping with the critical damping coefficient Cc, and in this zeta was is equal to 1. So the roots will be equal, of course. If zeta is 1, so 1 minus 1 it becomes 0. So the solution that we get is in this way, which is a plus bt e raised to the power minus omega nt. So here also we see that what is happening, the decay is there, right? So this is the kind of graph that we'll get. Now in practical cases, always we keep the damping factor somewhat greater than the critical damping. We actually want critical damping, but we have to keep into consideration that at times because of the temperature variations or other factors, the viscosity of the fluid may change. So it will actually bring the condition to the underdamping situation where the oscillation will be there and along with that damping will take place. But we don't want that. Rather we want the system to stop or the damping to happen in a very short duration of time without any oscillations, right? So we always keep this damping somewhat greater than that of the critical damping. You can take the example of a door. So if we slam a door, so what we want it to close, or we want the velocity to reduce to zero or negligible in very short duration of time. So if we are banging the door, we are closing the door, we want that in very negligible time the door should close. There may be AC on or there may be other Other conditions, like if you say that the system is underdamped, so what will happen? If you close the door, it will oscillate. So this oscillation can also, affect the person who's standing on some side of the door. So this is not what we want. We want that it should stop, it should close in very short duration of time and with the critical damping situation. Or we can also take the case of the cannon recoil or maybe the vehicle suspension system. So if the vehicle, if we want the damping in case of vehicle, we don't want it to oscillate, right? We want the damping effect to be such that in very short duration of time, the amplitude of or the motion, it should stop. So this is what is desirable. Therefore, in practical cases, the damping coefficient is somewhat greater than the critical damping system. That means zeta is somewhat greater than that of 1. In case of underdamping system, when xi is less than 1, we have seen that what exactly is happening? The decay is taking place with the simple harmonic motion, right? So at time is equal to 0, what is the displacement? Let's say that displacement is x naught. And after some time td. So td is what the time taken for the cycle in case of the underdamping system. So every time when going from 1 to 2 it is td, from 2 to 3, right, second to third oscillation it is td. So every time, for every cycle, the time taken is td. So if we want to find the equation for x1, we know the equation for shm. The maximum amplitude is what? X, right? So if it is in this way, right, and if the angle is phi, so this is what for this x. So this is x cos phi and we are taking the vertical displacement, so it becomes x sin phi. So the maximum vertical will be x sin phi. So this is what? This is x sin phi. So x1 can be written as x sin phi into the factor of underdamping system that is showing the decaying, that is this factor, right? If you remember, we solved the equation in two parts. One was showing the SHM part and one was showing the decay part of the damping, right? So this is the equation we can write for the displacement, maximum displacement at some time td, right? So if we move on to the next cycle, so x2 can be written as, because if in going from this x naught to x2 it has taken time td, so from going from t2 to t1 to tt it will again take this time td. So x2 becomes x e raised to the power minus xi omega n 2 td, because now time taken from going from 0 to 2 is twice of td, so into sin phi. Similarly x3 will be 3 times of td. Similarly, because we do not know how many cycles, how many oscillations will take place, so let's assume if some xn or xn plus 1 oscillations take place, so what exactly happens? Only the time changes, right? So for n oscillation it will be ntd, for n plus 1 it will be n plus 1 td. So in case if we want to find the ratio of two successive oscillations, it will be xn upon n plus 1 and e raised to the power xi omega n td, and it can be done for any successive oscillations, x naught upon x1, x1 upon x2, and sometimes what happens, the difference between two oscillations, it's very less. So at times it can also be done as, let's say if we want to find the value for x1 upon x3, that means we are finding the value for two oscillations. So the equation becomes x1 upon x2 into x2 upon x3, and that is how we can solve the values. Now till now what we calculated was for the linear displacement system, the linear displacement, linear velocity, linear acceleration. Now if assume there is a system having the rotational motion, the torsional motion is there, it is connected to the torsional spring and a dashpot, what will be the equation, right? So the moment of inertia of the system, let's say, is I, and the angular displacement is in this direction, which is theta. So same will be the direction of velocity and same will be the direction of acceleration. Now if this is the movement or this is the direction of velocity, the angular velocity or angular acceleration, the spring force and the damping force will act in the opposite direction, right? So the equation becomes we say mass into acceleration. So moment of inertia into angular acceleration is equal to, because both the forces are in opposite direction, and we are saying that for the equilibrium condition, the clockwise forces, the forces in one direction should be equal to forces in the opposite direction, minus, if let's assume the spring constant is given by k, so it will be minus k into theta, because theta is giving the angular displacement for the torsional spring, and minus the damping force, which is C. Now we know that the damping force is what? C into velocity. So what is X? If there is some angular displacement taking, theta is the angle with which it is changing. So what is the displacement? It is R into theta, sorry, R into, yes, R into theta will give the value of X, right? So what will be velocity? It will be R square into theta dot. So it becomes R square into theta dot, right? So we can write, if you want to replace this theta with some S, we can write the equation in this way, and we can find the roots of this equation and solve it accordingly. So no matter what the system is, the general form of equation remains the same. That is mass into acceleration plus damping coefficient into velocity plus spring stiffness into displacement. Now that can be linear or rotational motion.